Okay, so I go to the next part of this chapter 5. It's a very important topic, but this is the spirit of Math 4, mainly not Math 5, but it is included in Math 5 book, and that is under the title of Implicit Differentiation. Before talking about what is implicit differentiation, let us first talk about what do we mean by an implicit function, yes? So, let me just motivate you a little bit. So if I ask you to draw the graph of this, I can call this a function. Why is that? For example, I can say that f of x equals to x squared is a function. What do I mean by this? It means that if an operator is f is an operator, so that I provide this operator with the number x, and it provides me uniquely a number x squared. So that is the meaning of being a function. So that's important. If I have a machine f, it takes me an output, it provides me exactly a unique output. It takes me an input and it provides me exactly one output. Okay, so that is the meaning of being function. So in principle, whenever the input is determined, the output is already determined. There cannot be multiple values for one single value that I put in. So when I put 2, definitely I get 4. If I put the square root of 2 in, I will get 2 out, yes? There are no matter of confusions. So that is the meaning of being a function. Okay, how this idea reflects itself in the graph? When I draw the graph of this function, so you know that's a very famous one, so this becomes something similar to this. This means that whenever you choose your x value, the output value, which is y value, is uniquely determined. So what does it mean? How can you interpret this idea graphically? Every number x, first of all, every number x is defined, is acceptable for this function because the domain of this function is the set of whole real numbers, yes? And whenever I choose one number, any number x here, and if I ask you, do you know the output value, you would say yes. I will draw a vertical line here, I will find the intersection and read the y coordinate. That is the unique output for x. So this means that if you draw any vertical line, it will intersect the graph of that function exactly at one single point. Okay, not more. So that's the meaning, yes? Okay, but let us consider another famous curve. It's also a curve here, of course. Just the famous one, probably a circle, okay? Or even circle is good. But circle is also a curve, but this does not represent a function. Yes? Because, for example, if I choose x to be, let me make it more explicit. Let me take the radius to be 1 and the center to be the origin. Hopefully you remember this is at the equation or an equation for this circle. So if you look at the points whose x and y coordinates satisfies this equation, then they are sitting on the circle centered at the origin with radius 1. Yes? But this relation, whatever this is, does not define y as a function of x. So don't think that because y is on the one side, y and x are mixed. This equation can also be viewed in this form. It doesn't matter. If I ask you what do you think about this equation, you would say yes, this equation defines a function. Yes, it's a mixture of x and y. And that's also a mixture of x and y. But then if you draw the graph of this, you will get this circle, but this does not define y as a function of x, because if I give you 1/2 to be x, and I put 1/2 here, this becomes 1/2 to power 2 plus y squared is equal to 1. and then it becomes 1/4, I move it to the other side, it becomes 3/4. And then if I ask you what y is, you cannot uniquely answer. You have to say square root of 3 over 2, but plus or minus. So this means that if I give you this point, the output is not uniquely determined, yes? You don't know if that is, well, of course both of them are acceptable, and that is understandable, because if I draw this vertical line, I will have two intersection points. So this means that this graph does not represent a function, but this graph represents a function. And then we talked about limits of functions, derivatives of functions, integrals of functions, yes? So in principle, we cannot take the derivative of this relation, yes, because that relation is not technically a function. But on the other hand, what was the motivation behind the notion of derivative was to find the slope of the tangent line to the curve. The tangent line to the curve is still meaningful, yes, because you have a circle, but still you can draw a tangent to the circle. Even though the circle does not represent a function, but there is nothing to be wrong about saying that let us pick this point and let us draw this tangent line. By the way, the notion of tangent was familiar to us from the circle rather than parabola. Yes? So we learned about tangents to circles first rather than learning tangent to parabolas. So the question is that, is there any other way to understand the slope of this tangent line? Is the motivation somehow clear? So the question is that I want to find again the tangent line, but the point is that I have something a little bit strange. This is not the type of functions that I have used to. What is the type of function that I have used to? Is the function where y sits alone on the left and your expression regarding x sits on the right. That is called explicit function. So it means that y is explicitly defined in terms of x. Yes? But this is called an implicit. To be honest, I shouldn't call it implicit function because that's not a function, but let me just implicit function. Let me call it. So implicit function means what? I have a mixture of x and y. Y is not expressed in terms of x. Yes? For example, this one is also implicit. But this can be turned into the explicit form immediately by moving x squared to the right. Yes? But can I write this implicit function in the form of explicit function? In this case, yes. What can I do? I can start from x squared plus y squared. X squared plus y squared is equal to 1. Then I would say that, okay, I move x squared to the other side. And then I take the square root, but I have to remember to put plus or minus, yes? But I get two functions, not one single function. And that is clear. If I take the positive sign, this will give me the positive y values. So this gives me this semicircle. Is semicircle a function? Yes. Yes? And then if I take the negative sign but not the positive sign, then it will give me this lower semicircle. Is the lower semicircle a function? Defines a function? Again, yes. But if you join them together in total, that's not a function. Okay? Okay, now to find the slope, I want to take the derivative of my function. If I ask you, can you find the slope of this one? You definitely say yes. How do you find it? For example, assume that you didn't know anything about implicit differentiation, and I ask you to find the slope of this tangent line. What you can do, you can change the form of this function to an explicit form and choose the proper one, because you are interested at this point. So you need to ignore the negative one, because the negative one gives you this curve, which is not relevant to your case. So you only need this curve. So you just ignore the negative one and work with the positive one as before. You differentiate this function, put the x coordinate in the derivative and you get the slope. On the other hand, if I ask you to find the slope here, you will do this process, and what happens? This time you choose the negative branch, yes? And then do the same thing, differentiate it and put this x coordinate in the derivative, you get the k value, and then the rest of it you already know, yes? But the question is that, if this is not possible, then what should I do? And then, so the most of this, that's the whole point of implicit differentiation. The point is that most of the implicit functions are in a way that you cannot solve for y. Simply we cannot. For example, if I tell you y to power 7 plus y to power 5 is x, what is y? We don't know. Okay, we don't know how to find y in terms of x, yes, because that's polynomial equation of 7th degree in y and we don't know how to solve it. But if I draw something like this, it might be a curve again in the plane and I can pick a point on it. For example, I can choose y to be 1 and then when y is 1, x becomes 2. So definitely, even though I don't know how this curve looks like, but I know that 2 and 1 is a point on this curve, whatever it is. And then I can ask the question, can I draw the tangent line? Can I find an equation for the tangent line to this curve, whatever it is, at this point? Of course, this is not possible, so there should be another way to do it if there is. And that is the notion of implicit differentiation. So it means that we want to find the derivative without writing y explicitly first, which in this case is not possible at all. Is that understandable? Yes or no? Okay, so that's the idea. Okay, and the idea is very simple. The implicit differentiation is actually a very simple task, but that is, you need to remember the chain rule. Here, what I am saying, let us go back to this simple model, okay? I go back here, x squared plus y squared is equal to 1. I would say that, okay, whatever x and y are, I am imagining that y is a function of x at the end. Which function, I don't know. But what I do, I will say that if this is equal to this, then its derivative with respect to x is also equal to the derivative of the right hand side. If this is supposed to be equal to that, then the derivative of that is also equal to the derivative of this. But the derivative of the right hand side is clear. The answer is 0, because that's a constant. The derivative of the sum of two functions is the derivative of each one of them individually, so it becomes 2x plus. The next one, can you tell me what should I write for the next one? Y is a function of x, even though I don't know which function. I couldn't solve it like that. But I imagine that's a function of x. Then what is the derivative of y squared? What is the derivative of u squared? What was the chain rule? The chain rule tells you what is the derivative of x squared. You know this is 2x. But in the chain rule I told you that if u is not x but a function of x, the chain rule comes in. What is the derivative of u squared?
2u
prime. 2u times u prime, where u is a function of x. Here y is the same thing. Y is a function of x. Yes? So when you differentiate it, it is not just simply 2y. It becomes 2y times y prime. Is that understandable? Okay. And then what I am looking for? I am looking for y prime. So I have to solve this equation and find y prime. So this means that my goal is to make y prime alone. So this becomes 2y prime, 2y prime. I move it to the other side. And then I divide by 2y. Considering that y is not equal to 0, then y prime becomes minus x over y. So that is your derivative you were looking for. Okay, of course, if you have a normal function like this, when I differentiate it, the derivative is expressed only in terms of x. But you shouldn't expect something like this happens for the implicit differentiation, because you started with a mixture of x and y. You shouldn't in general expect to get something only in terms of x for y prime. It's a mixture of x and y again, but that is your derivative. Okay? Let us try to motivate you that why this is, at least for this example, let us show you. I told you that let us do it directly. I mean, instead of doing this simple trick, let us just try to find y in terms of x. We already did it. We got two branches. One with positive and one with negative. Yes? Yes. Okay, now let us assume that this is the first scenario. Let us check. Let me calculate the derivative of y. There is nothing hard about this. You have studied a lot about this in Math 4. So what should I do? The derivative of this is 1 over 2 square root of this expression, but multiplied by the derivative of this expression. This is not implicit differentiation. This is the chain rule. Yes, as you studied in Math 4. But the derivative of this is what? Is minus 2x. And then minus 2 and 2 will be simplified, so minus x will be left. And this is your derivative. Yes? But in this case, number 1, there is another name for this. What is that? It's y. So it becomes minus x over y, and that is your answer that you got there. You might say that how we know that the other branch is not the case. Let us check. The other branch, take the derivative, it becomes negative 1 over 2 square root of 1 minus x squared multiplied by the derivative of that one. But then this becomes minus 2x positive and 2 are cancelled, so it becomes positive x over square root of 1 minus x squared. Yes? But now you are working in the second branch. In the second branch, the square root of 1 minus x squared is minus y. So I take this again, I put minus y. I get again the same answer. So it doesn't matter which branch you are working. You see that the answer to y prime is in both cases are the same. And that is exactly the one that we got without going through this process of finding y first and then differentiate. In this case, at least two methods are possible. Method of implicit differentiation is possible. Method of direct finding the explicit function first and then the differentiation will work. But for example like this, there is no hope at all to be able to find y in terms of x. Either we should leave the problem totally, or we have to use the implicit differentiation, which is possible in this case. Okay? Is that understandable? But for example, can you tell me how to differentiate this, by the way? So we want to differentiate this implicit function. You know that implicit function, so this means that that curve, whatever it is, you can restrict yourself around the point of interest, then you can cut one part of that, which is a function, yes? Let me also motivate what I mean. I mean that if you want to find the tangent line at this point, you really don't care about what is happening far away. You can just cut this part, and that part is always a function, yes? So I don't know if the function is also complicated, I mean, yes, I don't know. For example, if I want to find this branch, so here this is not a function because you see vertical lines intersect a lot of points, but if I want to find the tangent line here, I really don't need to focus a lot. I just need to cut this part, and then this part is just a function. Yes, but the point is that I cannot find an equation for that function easily. But I don't need if I can calculate using this rule. So let us go back here and calculate it together. Okay, so what you do, whenever you see y to the power of 7 plus y to the power of 5 is equal to x, so you start differentiation. And that is, by the way, always a convention that y is the vertical axis, x is the horizontal axis. Y is supposed to be a function of x, not the other way around. But that's convention, of course, in mathematics. Okay, so if I differentiate, the right-hand side is clear. But can you tell me what is the derivative of the left-hand side?
7y6 multiplied by y prime.
Yes, 7y6 prime plus
5y4 multiplied by
y prime. And then what is my goal? My goal is to find y prime. So I have to make y prime alone. So what I do, I factor y prime out. You don't need to be worried about if you can factor more. You don't need to care about that. It's equal to 1. But I am looking for y prime. So y prime becomes the right hand side divided by 7y cubed plus 5y4. Yes? That is your derivative. Yes? Okay. So let me give you some exercises. Okay, so for example, let me just pick this, by the way, this is the book that you will start studying soon. So let me just take this example. Okay, let me first give you an example. So I have this curve, x sine y plus y cosine x is equal to 1. First of all, I want you to understand, by looking at this, you realize that you are facing an implicit function, yes? Because you have a mixture of x and y next to each other, yes? And then I am asking you to find y prime. Okay, so how can I do that? X sine y plus y cosine x is equal to 1. It's nice. I just want to check Geogebra. If Geogebra is capable of drawing implicit functions, you will check. Okay, so how do you do that? I take the derivative from both sides first. So the derivative on the right hand side is 0. So if you don't mind, let us be patient for the time being and take the derivative of this combination and do it step by step. Okay, now tell me what to do. You see a sum and you want to differentiate the sum. So what is the rule? I have to differentiate the first part plus differentiate the second part. Yes? But what rule is needed for the derivative of the first part?
Equals to 1.
No, I took the derivative.
Okay.
Yes, we have to take the derivative. That becomes 0. Okay, and then what rule is important here? What rule applies actually, not important. There's only one rule that I can apply here. Yes?
Product.
The product rule. So this means that, let me write everything in detail. The derivative of the first one multiplied by the second one plus the first one multiplied by the derivative of the second one. That's the product rule. The same thing applies here. The derivative of the first one multiplied by the second one plus the first one multiplied by the derivative of the second one equals to 0. I have to continue until there is only one prime left, and that is y prime. Okay, but we know that x prime is 1, multiplied by sine of y is sine of y. Okay, now I want to ask from you, what is the derivative of sine of y? You should always think that y is a function of x. So what's the derivative?
Cosine y multiplied by y prime.
Yes, cosine y, let me put this dot multiplied by y prime, and then y prime cosine x, and then minus sine x. Yes? It doesn't matter how complicated the equation become, it is always there is one y prime in some of the terms. You factor it and just move the other part and then divide. It doesn't matter how complicated it becomes. So I will just take these two and take y prime out. So this becomes x cosine y plus cosine x times y prime. And the terms without y prime should be moved to the other side because the goal is to make y prime alone. So this becomes y sine x minus sine y. And then finally, if this expression is not 0, I can divide by that and I get this result. So y sine x minus sine y divided by x cosine y plus cosine x. Yeah, you shouldn't expect more than that. That is your derivative. Okay? Okay, let us first check GeoGebra if we have... so might be this function is a little bit crazy. Let me just draw these two. So can you remember them? So x sine, and okay, I will try to remember. Let me... Okay, so let me see if we need some comment, or let me type this first. Y to the power of 7. No, this is not so. Oh, it is Swedish keyboard. So y to the power of 7. What was that? Plus y to power 5 equals to x. Yes. Yes. I don't know. So that is the graph. But by the way, this is a function. Yes, is that right? But so you see that this is indeed a function. But let me make it even power. We should be able to predict that this is a function. It's not hard mathematics. But let me make it even power, for example 6. Then it is not a function. Yes? Because you see that some vertical lines does not intersect, some vertical lines don't intersect this, but some of them intersect more than one. Yes? So let me see, if we zoom in, what happens. Is there something beautiful coming out? Okay, but the behavior is strange. Could you predict that something like this part will happen? Yes. Yeah. I mean that this is a function, and you can talk about its properties, of course. So, but let me, the other one, what was that? Do you remember?
X.
X what?
X sine y.
Sine y.
Plus y.
Yes.
Cosine x.
Sine x.
No, cosine x.
Oh, cosine x. Cosine x
Equals to 1.
equals to 1. Okay, so that is the function. By the way, I have... Oh, there are many interesting things coming in. Yes. So this is your explicit function now. Could you predict something out of it? Yes or no? Because somehow we should expect something like this, because sine and cosine are periodic functions. So somehow they will start repeating themselves. So you shouldn't expect... I was a little bit surprised when I saw that this graph. First of all, because I didn't see that part. I just saw something like this, I don't know. But it's very strange that this doesn't repeat itself, because sine and cosine are periodic functions, so they start repeating themselves. So the pattern should be more or less clear. For example, could you predict that the origin is not on this curve? Yes, because 0, if I, instead of x and y I put 0, the left hand side becomes 0, the right hand side becomes 1. Okay, but I don't know. Let us see how it goes. Of course, unfortunately, I have to close this one. That is good to describe things. Let me just do that. Okay, so can you tell me a point on this graph? We can go back and explore it and make it a little bit fun. So, can you give me a point which is on the graph, and I want to find an equation for the tangent line at that point. So for that one, I ask you to give me a point that you are sure lies on the graph. Yes? So, can you tell me a point? It's not easy, by the way, because so can you give me a point? I don't know how. Because you need to give me a number for x, for example. Then, of course, that is not a simple problem to solve, yes? Because I don't know, how do you want to find a point on the graph exactly? Huh? Yeah, one of them is easy, yes? If I put x equal to 0, yes, that is working. That's all. We are lucky a little bit. If I put x equals to 0, then what happens? It becomes 0 sine y plus y times cosine 0 is equal to 1. Yes? And then this part is 0, this part is y is 1. So this means that 0 and 1, I don't know, is it confirmed that, yes, 0 and 1, x0, y1 should be a point on the graph. Yes? Is there any other point we can say y0, x1? That's also one point, yes? Okay, but let us stick with this one. How can I calculate the k value? So for calculating the k value, I have to refer to the derivative. In the derivative, I replace xy with 0. Yes? No, sorry. X with 0, y with 1, and put it here. So the k value becomes y is 1, x is 0. Okay? X is 0, y is 1. Yes? Do you agree? Okay, so then let us calculate this. Cosine of 0 is 1. This is gone. Sine of 0 is 0. So this is minus sine of 1. But what is 1 here? Is it 1 degree or what? It is radian. Because these formulas for the derivatives are only valid when we are working in radians. So that is minus sine of 1 radian, which is approximately 57 degrees or 57 or 53, I don't remember. So that is the k value. And then I would write my equation, y minus y node is equal to k, x minus x node. Y node is 1, so this becomes y minus 1. K is this number, minus sine of 1 radian, and x minus 0. And I don't know if we can write it better. So this becomes minus sine of 1, whatever it is, multiplied by x. Then I move minus 1 to the other side. So this is an equation for your tangent line. So, but of course, it is, so you see, this implicit function had a lot of branches. But this is not tangent to all the branches, and you shouldn't expect that. It is tangent around the point that lies, so around, for that branch which contains this point, in its neighborhood. Yes? So that is the meaning of being tangent. So it means that from that complicated picture that you saw, there is one branch containing this point, in principle. We go there, and around its neighborhood, this line is the tangent to that function. Yes? So, let us, by the way, check this if that is also correct. Okay? That is also a good idea to check that one as well. Oh, I have to go here. Then I have to go down. Okay? Okay, so that is our graph. By the way, so what was my point? My point was 0, 1. So I can type it. A equals to 0 and 1. Where is the point? Oh, it's here. It's this blue dot here. Yes? So, and then I don't know if Geogebra can do that. We are asking a lot from Geogebra, yes. So let me see. We go here. There should be a tangent line somewhere. Yes, tangent. And then I will do this. Oops. Every one is chosen. And then the point. Yeah, it's very good software, by the way. So this is the tangent. So you see, this is just tangent to this branch around that point. Is that understandable? It is cutting a lot of other branches. But I want you to understand what is the meaning of this. Yes? And I don't know why Geogebra doesn't change the colors. So let me change the color, for example, to this. Oh. That is the, no, that's not a good color. Let me make it red. So I hope that it is visible. Okay. And then you see that GeoGebra has provided us with this equation for that line. But if I have done it right, that should be my equation. How can I change to radian mode? Do you remember? Do you know by heart? Where is it? Settings. I hope this is already expressed in radians. Let me see my chances. Okay, y is equal to, so let me now clean these. I don't need them. I don't know even what they are. Okay, so that is my tan. So sorry, that was the, so these are, I don't know what are they. These are also equations of lines that you see here, but can you see why we have so many lines involved here? Anyway, so that was minus sine of 1 radian times x, do you remember, plus or what? Plus 1, yes? Oops. So my calculation is wrong. Yes? Because this is not a tangent line. The problem is that I should write it in radians. I think this is set up in degrees. Okay. If I want to make it in radian, this is 1 degree. I want to change it into radians, so it should be pi divided by 180, yes? So what is pi? Let me fix it. Pi divided by 180. No, it's not working. It's up. It's very strange. Do you see where did I make a mistake? Because this doesn't show that. Yes? Let me see if I have done everything right. Might be we have done the derivative wrong. I don't see any other.
Maybe Dima is saying that try that's in instead of you've written radians in radians again. Try
No,
to
but
count.
So what should I do then?
What was it? 57 degrees.
That's the point. I don't remember exactly, but there should be a way. Don't you work with the software? So because I'm not, this is not the software that I usually use. I use Matematika. But do you know how to change from degrees to radian?
You have an option when you press the 3 dots. There's an option that's setting.
Here.
The one you just did.
So let me. There should be something here, but this I know is degree. Yes.
But when you deleted it, the menu it had a settings option.
Okay, let me just do that again. 1 is equal to minus. So might be I have done the calculation wrong. Who knows? So sine of 1, and then let me put the multiplication as well. Might be this doesn't understand that one. Multiplied by x plus 1.
No, that's
The dots.
So don't delete it. Just erase and put the cross. You did like decimal points instead of multiplication. Now.
Okay. I understand.
And
So-
then up besides the 9.
Okay, so now I understand it is expressed in degrees.
And
So
then
let me, yes?
If you do
Now it is correct.
180.
No, it's correct. No, because usually it should be automatically in radians, not the other way around. So I think this cross, I have to write that cross somehow. Now this is the curve, yes, because let me clean it, yes, that's correct. So what we calculated is exactly this line. So you see that implicit differentiation is really powerful, even though there is a mess of curves going around, but if you pick the right point using the implicit differentiation, we were exactly able to find this line. Yes? So, is that understandable? Yes? So that is the idea of implicit differentiation. Okay. So I have to make myself a little bit faster when I'm typing in Geogebra. So I have to respect all those things. Okay. Yes. But of course we can solve diversity of problems now. Let me just choose some of these problems. Okay, so I will actually stop here. Let me choose one of these problems and try to solve it together, okay? Yes. The question is that you are supposed to find an equation for the tangent line of the given following curve at the given point. So I want to challenge you a little bit about your differentiation skills. I want to see if you have forgotten or not. So tangent of xy squared, then I want to check your answer using Geogebra again to improve my skills as well, okay? So then this is equal to 2xy divided by pi, and the point is minus pi and 1 over 2. Yes? Yes. So this is supposed you are supposed to find an equation for the tangent line which is tangent to one branch. I don't know how many branches are there here, but the point is that, do you think this point lies on the graph? This is important to check always. Because do you remember, if the point does not lie on the graph, the method of finding the tangent line is a little bit different. Okay, so this point should lie, and this point should be the point of tangency. Let us check. On the right hand side, instead of x, I put minus pi. That pi and that pi are cancelled, so it is minus 2 times y. Y is that one, so it becomes minus 1. Yes? And then that is also minus 1. Why? Because y to power 2 is 1/4. Multiplied by minus pi is minus 45 degrees. Tangent of minus 45 degrees also minus 1. So this point is really on this curve, wherever it is and whatever it is. Okay, now we want to calculate an equation for the tangent line. So I want to keep this for you, okay? We have a little bit of time. I give you 5-6 minutes, so, and then you do it. And then you give me your equation, we write it down, check it using Geogebra. Yeah, I'm interested to see how the graph looks like. I hope that you have the formulas in your memory, otherwise you can ask me which formula you need, I can write it on the board. But you tell me which one you need. So that formula is, I think, the only formula that you might have forgotten, yes? But the rest of it, I think you should remember it in principle. Okay, any progress, because we want to finalize the problem. So at least you can help me to do. Okay, so what I'm supposed to do, the first thing that I do, in my head, I will get rid of this fraction in a way. Of course, you see, if you want to do it, this is just 2 over pi, which is a constant, and I don't care, and I write xy. This is the way I think about it, okay? And then you differentiate both sides, so if you don't mind, let me not repeat everything again, so I put a prime here. Yes? I hope that you don't have any problems with the right-hand side. 2 over pi is a constant, we don't care. Just write it there. But this is a rule. What rule is that? The product rule, yes? So this becomes the derivative of the first one, 1, times the second one, plus the first one multiplied by the derivative of the second one. But the derivative of the second one is y prime. Agree? The left-hand side, now you help me. You see, tangent of u is this. So it becomes 1 over cosine squared of xy squared, but multiplied by u, which is xy squared, prime. Yes? And now what you do, there are no primes here involved, so I just copy and paste this part. But then again, I face another product rule. The derivative of the first one multiplied by the second one, plus the first one multiplied by the derivative of the second one. The derivative of the second one is 2y, y prime, and x. So 2x, y prime. Yes? And then what happens on the right-hand side, it's 2 pi y plus x, y prime. So this is for the time being. Okay, by the way, let me also teach you a shortcut. I told you that you're supposed to find y prime. The question is not find y prime. The question is to find the k value. So, of course, you can do this algebraically, find y prime on the left-hand side and everything there on the right-hand side. You can do these manipulations, but at the end, what you are supposed to do to put numbers instead of x and y. And if you want to put numbers, instead of doing all those messy calculations to find y prime, you just put the numbers right here. You understand what I mean? It doesn't matter. If I ask you to find y prime, of course you have to find y prime. Yes. But if I ask you to find the k value, which in this case I want, because I want to find an equation for the tangent line, I really don't need to spend some time on it. Yes. So just put these numbers in, and most of them try to do it in your head. Yes. Y is 1 over 2. Remember. So when I put it here, it becomes 1 over 4. X is minus pi. So it becomes minus pi over 4. But for cosine, minus and positive are the same, so it is cosine of pi over 4. You remember what that is? Cosine of pi over 4 is 1 over square root of 2. And then you raise it to power 2, so it becomes 1 over 2. But because 1 over 2 is in the denominator, it goes to the numerator and becomes 2. Yes? So these calculations you can do. So the first thing is 2. And then I go here. What is y squared? It is 1 over 4. And then plus 2 times x times y. If I 2 multiplied by x is minus 2 pi, multiplied by y is minus pi, multiplied by y prime. Yeah, please check my calculations because we want to have some fun with Geogebra. So do you confirm that calculation? And I hope that you agree this is much easier than trying to find y prime algebraically and then substitute the numbers, yes? Okay, so then on the right hand side 2 pi, 2 over pi, and then what I have y, which is 1 over 2, and then x times y prime, so it is minus pi y prime. Anyway, there is only one unknown left for me here, and that is y prime, and I am supposed to find that. But let us check that I have done everything right. Yes. Okay, so what can I do? I multiply, first of all I can simplify this 2 with that 2. This becomes 1 over 4 minus pi y prime. On the right hand side 1 over pi, I multiply it in, it becomes 1 over 2 pi. 1 over pi multiplied in, it becomes negative y prime. So then I move y prime to the left, so it becomes positive y prime minus pi y prime. I move 1/4 to the right. And then I want to make y prime alone, so I have to factor it out. I don't know, this, yes, we can keep it like this, yes. Well, let me simplify that. So 4 pi, we take the common denominator 2 times, so it is 2 minus pi. Anyway, this is not that simple, but anyway, y prime is 2 minus pi divided by 4 pi, 1 minus pi. This is y prime, but y prime is not a good name here because after I should have replaced y prime with k value, because what I get is the k value, not y prime. So that is my mistake. When you put the numbers in, instead of y prime, you have to put k value, yes? But the k value becomes this. And then the point is here. So what is the formula? What is the formula for the tangent line finally? Let me just do it quickly, and I appreciate if you can write it because then I cannot memorize it. Y minus y naught, which is 1/2, is equal to 2 minus pi divided by 4 pi 1 minus pi and x minus minus pi. It's a little bit complicated, but so y becomes 2 minus pi divided by 4 pi 1 minus pi x, and then I multiply pi here, this pi cancel that pi, and then I move 1/2 to the other side. And if you want, yes, we can simplify this a little bit, not that much. So I can take the common denominator to be this guy, and this is 2, so let me write 2 minus pi, and this is 2 times 1 minus pi. And finally, if I have done every calculation right, that should be the final answer. So there is an x missing here, sorry. So 2 minus pi divided by 4 pi 1 minus pi x, and then 4 minus 3 pi divided by 4 1 minus pi. Yes, so that is the formula that we got. I don't know if this makes sense or not, but that is the formula we got for an equation of the tangent line to some branch of this. So if I want to be careful, so one thing that you learned is not to spend a lot of time to do this algebraically, because your goal is to find the k value. But remember, my mistake was when I put the numbers, I have to replace y prime with the k value. That is not the y prime. Okay, so let us see how it goes in GeoGebra, and then we are done. We continue a little bit about this next time as well, okay? Okay, so the formula that was given in the book was tangent, and please see that I am not doing something stupid here. Okay, and this is equal to 2xy divided by pi, oh sorry, I have to put equality here, equality, and then pi. Oops, it's really a strange picture, so I don't know what that is actually. Okay, we can zoom in a little bit to see if something interesting happens. I mean that this is very hard. We can also check Wolfram Alpha. I don't think we get any clue here. Yes. So this is the ant army. Yeah? So and then let me just put that point here. Let us see how it works. The point was a equals to the point minus pi. Oops. So a is equal to minus pi, comma, 1 over 2. That is also my point, and I don't know where this point is. Okay, so it is on this branch, you see? So we can forget about everything else. So this is here. Okay, so let me zoom in a little bit. No, if I zoom in, it cannot calculate so fast. Okay, so let us just live with it. Okay? And now can you just read that messy formula?
Yeah. Y equals to
Yes?
2 minus pi.
In the numerator.
Yes.
So I have y 2 minus pi, and then divided by
4 pi.
4 pi,
Parentheses 1 minus pi.
1 minus pi.
And then x.
So let me this time put this multiplication by x.
Yeah.
Yes?
And then plus.
Plus
In the numerator, 4 minus 3 pi.
3 pi.
Divided by 4 parentheses 1 minus pi.
I don't have any clue. Oops! Fantastic, yes? So it is just the one that we calculated. Can you see that? Let me change the color. Yes. So I don't know, can I... So, but this is a little bit... But I hope that you agree that somehow this is not done randomly. So if we did the calculation, so this means that you see, we can also check this with Wolfram Alpha. I don't know if that can draw better, but might be that it needs heavy calculation. So this, it doesn't matter how I zoom in. Let me see if it changes something. Yes, it changes good. So I mean that I can just move this a little bit. So you see that this is the tangent line, but do you think, it seems that there is an inflection point there as well, yes? No? No, it doesn't matter how much I zoom in, I cannot see something beautiful there, but anyway. So I hope that you at least are convinced that the calculation is correct, and then this becomes tangent to one part of this one of the branches here. Okay, any questions? Okay, we will continue a little bit with this notion. I think that's also nice. Thank you.